Hello, stats students. It is time to wrap up Chapter 6 in Statistics, 6-4, very wordy title, The Normal Approximation to the Binomial Distribution. So we are going to talk and do a quick refresher. Remember binomial distributions. I don't even know if you remember these 4 characteristics. This was from section 5.3. Remember, Chapter 5 was all about binomial distributions and how we liked them to be normal, right? So we're going to intermix those two things. So first of all, our 4 characteristics. The first characteristics, you have to have a fixed number of trials. Remember, we did that one activity with what if you guess on a multiple choice, 10 questions, so there were 10 questions. The outcomes are independent. One multiple choice question does not affect another one. Our experiment can only have 2 outcomes. You're right or you're wrong. It's good or it's bad. It's up or it's down. It's on or it's off. There's 2 possible outcomes. There's no partial credit here. And last but not least, the probability of success remains the same for each trial. So if we're looking at a multiple choice question with 4 answers, you have a 25% probability of guessing correctly. Remember, probability of success is P, probability of failure is Q. And then that's section 5.3. Then we run down and we add one more thing. If we're going to use this binomial distribution, but we're going to use it with a normal approximation, we have to have these 2 things happening. And I don't like how I wrote the second one. Do you probably remember, though, right, that mu is equal to n times p? That's how we found the mean in a binomial distribution. And sigma is equal to, so standard deviation is equal to n times p times q, and then take the square root of it, because remember, variance is just a tool to get us to standard deviation. So those things we all did back in Chapter 5. Well, now we're going to recycle these ideas and use them with a normal approximation. Remember, normal is a bell curve, a normal distribution. So let's talk about a few things. I've got very important things to put up here on the board. The first thing is when your n is really large, like 100 or more, sometimes it is tricky, difficult, tougher to use to find all our data. So we can use a normal distribution to approximate our binomial distribution. Remember, binomial distribution, 2 possible outcomes. So very large sample size. When the probability of success is close to 0.5 or 50% probability, the shape of a binomial distribution is pretty normal. We didn't look at that specifically, but trust me. We can only use the normal distribution. We're going to have some steps that we have to go through. We have to check this first. This is like our check step that says that we're allowed to go forward. N times P has to be greater than or equal to 5, and N times Q has to be greater than or equal to 5. This, I'll even put a little note, is going to be step 1. And last but not least, this wonderful table that I have incorporated in here, you must use this continuity correction table when you are in this section. Here's the reason. Because remember, discrete and continuous variables, discrete is counted, continuous is measured. Continuous are those ones that we can have all those in-between things, and perhaps we rounded them. So it's not a discrete situation. So we're going to refer to this table every single time, and this is going to be in step 4. So table, refer back, step 4. So we just have to be careful about what we're finding because of that whole rounding error situation. It's not just counted variables, it's a lot of in-betweenness that ended up getting rounded. So I'm going to just use this. We'll come back to this when we're ready. Let's go on to our steps. So here's how we're allowed to do this. This is what we're going to go through for each problem. 6 steps. Everybody enjoys a lot of steps. So step 1, I already told you. Check to make sure your normal approximation can be used. So check to see If n times p is greater than or equal to 5, check and make sure that your n times q is greater than or equal to 5. It doesn't have to be anything super formal. Do a quick check on your calculator and make sure. We all know that n is our sample size, right? And we all know what p and q is, probability of success and probability of failure. Second step. So if 1 doesn't happen, stop where you are, it's done. So the second step, find the mean and the standard deviation, which we just said. We already know mu is n times p, right? So you already just checked that to make sure it was greater than 5. We know that standard deviation, sigma, is our square root of n times p times q. Again, we did that back. I put this little thing over here in section 5.3. So if you can't remember doing those, then feel free to check back. Once you've gotten your mu and your sigma, you need those in your calculations. Then we're going to write our problem out in the technical format, probability notation using x. We kind of throw this in here sometimes. When I say probability notation, I might be say, find the probability that x is greater than 9. Or find the probability that x is greater than or equal to 9. It's going to make a difference when we go to our continuity correction table. But this helps us to match it up. Once we've got this helps us. So step 4, use that continuity correction factor. Show the area corresponding under the normal distribution. When I say to show it, you know me. I'm saying couldn't hurt to draw it. Some people aren't going to need to, but if you ever ask me a question, I'm going to tell you, what does that look like? So let me jump back for just a second because I used this example p is less than or equal to 9 to get from step 3 to step 4. P is less than or equal to 9. So I'm going to look in this table. P is less than or equal to some number. We said less than or equal to 9. So when we use this in the normal distribution, I'm going to say I have to actually use in my calculation when I find z-score, I have to actually find p of x is less than my value 9 plus 0.5. So 9.5. If I had just left it as p is less than 9, you know how I said that first? X is less than 9. So that falls right here, right? X is less than some number a. So then I rewrite that. So I'm actually going to use the probability that x is less than 9 minus a half, so 8.5. Again, when you draw it, you'll kind of see why we did that. We have to take into account any rounding. So that's how that table works. Take a quick look at it. Let me know if you're struggling with it. All right, so once we've got our continuity correction, then comes the real thing. Find the z values. Do the z-score formula. So z is equal to x minus mu all over sigma. I forgot we were working with populations. I believe that was in section 3.3, and I know for sure we did that in section 6.2. And then last but not least, we need to find our solution, aka the area under the curve. Remember, we've shaded, we've decided, do we need to subtract from 1? Is it a between problem? This is section 6.1. So we do step 5, that's 6.2, because we're converting from raw data to z-scores so we can use our z-score table. So let's do an example. All right, I know it's a lot. I laid it out in steps just to make sure. So, population of college cities. College students often make up a substantial portion of the population of college cities and towns. State College Pennsylvania ranks first. 71.1% of its population is made up of college students. That's a huge population. Imagine when all the students go home, right? What's the probability that in a random sample of 150 people from State College, more than 90 are not college students? Well, first of all, I want to cross out the not. I should have taken that out. More than 90 are college students. So I want to think about a few things here even before I start going through the steps. I want to ask you, what is our probability of success? So what percentage or probability are college students? 71.1%, right? I'm going to just write that then as a 0.711. Turn that into a decimal. If P is 0.711, what does Q have to be? Subtract from 1, what do you get? 0.289, I think it is. And the other thing that I probably need to know is N, what is my sample size that I'm working with? It says, what's the probability that in a random sample of 150 people? So those are all important things to know before we even get started. We're going to need those as we go. We can talk about the other stuff as we work. So, also I wanted to mention, right, this is a binomial situation. You're either a college student in town or you're not. So it's two possible outcomes. And also notice our sample size is 150. That is quite large, typically over 100, typically. There's always exceptions to every rule, right? Okay, so let's see if check if our normal approximation can be used. So basically we want to make sure that n times p and n times q are both greater than or equal to 5. Well, now you probably realize why I wrote down p, q, and n, right? So n times p, 150 times 0.711. Is that greater than 5? I believe it came out to 106 point something. N times q, 150 times a 0.289. Is that greater than 5? I think that came out to, got 43.35. These two numbers, by the way, should add up to 150, right? Because it's the whole. So yes, check. We can use the normal approximation. If I got less than 5 on either one of those, I'm in trouble, and you're going to ask the teacher what's happening. Step 2, find the mean and the standard deviation. This is a binomial situation, so mean is equal to n times p. We just found that. We found that n times p was 106.65. Careful, because we just found something really important. When we go and do our calculations with our z-score, we now know mu. We also need to find our standard deviation. So sigma is the square root of n times p times q. So basically, n times p times q will be 150 times 0.711 times 0.289, and that's variance, so I'm going to square root that at the end, and I believe that's going to come out to something like 5.55. So that's an important piece of information because we need that when we figure out our z-scores, right, our z-values. So step 1 is making sure we're okay. Pre-step 1, I found p's, q's, and n's. Step 2 is just finding more stuff that we need. Write the probability notation that models the problem. So I'm going to draw myself a really teeny tiny, over here, normal curve. I know my mu is in the middle right here. My mu we just found is 106.65. Right? So we want to know more than 90 are college students. So let's see, if I figure 90 might be about right here, more than 90 has to be shaded to the right, right? That's greater than. So what's the probability that x is greater than 90? So flip back. That's not where we're leaving this because we have to go to, now in step 4, we have to go to our continuity correction table. X is greater than or equal to 90. So I'm going to flip back here even though I lost a bunch of stuff. Greater than 90. So right here, this guy, number 3, right? Probability that x is greater than 90, so my a value is 90. That tells me when I do this, I take my a value plus 1/2. So the probability that x is greater than 90.5. So watch that. It tells me to add 1/2 to it. Let me scooch back. Because it's greater than, really, all these things would round back to 90, right? So we're still including those values in there. So we said this is actually the probability that x is greater than 90.5. At this point, step 3 becomes obsolete. I use my numbers from step 4 in my calculation. All right, so now let's do some work. So it says we need to find our z values. We have everything here that we need. We actually calculated them this time instead of just being given them. So let's see. Z is equal to x minus x bar all over, or sorry, x minus mu all over standard deviation. So we're going to use this 90.5, right? That's our value. Minus mu we found was 106.65. Divide that by our standard deviation, 5.55. And when we calculate that out, I believe that's going to be is that a negative 2.91? Not my final answer, right? This is a z value. Once you know your z value, right, find the probability. Whenever it asks you to find your probability, you go to your z table. Basically what that's saying, if this is mu equals 0, we're looking at a negative 2.91 for our z-score. So I'm going to go to my z table. I'm going to look up negative 2.9. I'm going to scooch across to 0.01, and I'm going to get 0.0018. 0018. But here's the thing. Watch the shading. We've been doing this all chapter. This part to the left is 0.0018. I want to know greater than, right? So what's greater than? We have to subtract from 1. So my final shaded area that is greater than 90, taking into account the continuity correction value, is going to be something like 0.9982. So I could say the probability that x is greater than 90, taking into account the continuity correction factor, is 0.9982. Or 99.8%. Looks like it, right? It's a huge percentage, especially when you know the standard deviation is almost 3. So that is it. We won't do, I don't think there's another example. That is it for section 6.4. We'll practice these more, I promise. Thanks for hanging in there. See you later.